Hello YouTube, RJ. In this second part of our Intro to Digital Electronics, we're going to go now where we looked at the 595 chip last time, talked about zeros and ones. We're going to jump in the data sheet, go through and show you some of the important specs in a data sheet for your digital components when you're designing. And then we're going to jump over and take a look at a schematic I put together for the little circuit we're going to build, and we'll talk about how we hooked everything up in that. And then that's going to lead us into the follow-up video, number 3, which will finish up this intro, where I'll go ahead and build that. We'll talk about the little bit of software very basically that I wrote to run everything, and we're going to go over to the bench and we're going to look at this in operation, and I'm going to have the controller send data very slowly so that we can actually watch data move through these chips and actually let you really see the physical outcome of the theoretical we've been looking at, and see that when we think about the theoretical of what's going on, the physical will follow it. Now often, you're running these things at real high speed, you couldn't see that, but I'm going to run this real slow. We're going to clock the data in and out and cycle the lines really slow, and you're going to be able to see the data move. Hope you enjoy this. Let's get over to the computer. Okay, welcome over on the computer, and we've got the data sheet for a CD74HC595, or aka our 595 chip, 8-bit shift register with 3-state output registers. So don't let the 3-state throw you. We'll talk about that. In the previous video where I talked about ones and zeros, I left the third state out intentionally. I thought this would make it easier if we kind of eased into third state in this video. So let's point out a few key things on this data sheet. One is that this has a wide operating range from 2 volts to 6 volts. That's the range of voltage operating the chip that you can operate at. Notice also that we say we have plus or minus 6 milliamp output drive at 5 volts. Okay, first of all, why plus or minus? Well, you've got multiple states on your outputs, and that's what they're talking about. Bear in mind, if we have a 0 on an output, we don't just not put voltage there, we drive that to ground. So basically we can sink current. If something applies voltage to this line, it can sink it and bring it down, try to get it down to 0. So you're driving both directions. And because of that, you can sink current or you can supply current. So you can source or sink current. So that would be a positive or negative current flow. So that's why they say positive or negative 6 milliamps. Output drive at 5 volts. Now, does that mean that these outputs can handle 6 milliamps? Well, it does, but it doesn't mean that's the limit of them. That's not what they're saying. This confuses people. They think, well, you can't drive at 6 milliamps on these outputs, but that's not true. That doesn't mean that if you're running the chip at 5 volts, you can't sink or source more than 6 milliamps. What that means is that if you're driving a 1 into a load of 6 milliamps, and the chip's at 5 volts, you can get 5 volts here. If you increase the current draw, this may not be able to hold the voltage at 5 volts. It'll start sagging on you. They're just telling you that you can get the full 5 volt output here up to 6 milliamps of draw. If you're going to draw more than that, expect the voltage might not be the full 5 volts. And we're going to show you they have some more detailed specs later on talking about the different voltages you could expect at different outputs. So let's go down and take a look at the description. The CD74HC595 is an 8-bit serial input parallel output shift register with output registers and a 3-state outputs. Down here you're going to have device information. Notice that the difference in these part numbers are the last letters, and it denotes what package. For example, we're going to be working with a DIP package. So one of the part numbers we might be working with is 595E. If it was a DW, then it would be an SOIC, a wide. Typically what DW means is it's a wide package. Look here, it's a wider package. Because they have an M, which is an SOICD, which is the same chip but not as wide a package. Then you have an SO, then you have an SOP. This tells you what part numbers are what packages and what body size, the nominal body size. Should be familiar with this diagram. We used it in the last video to describe the operation of the shift registers and the storage registers and how all of this flowed data. So let's go down to pin configuration. Note down here that it explains that all your different packages have the same pin layouts, which is nice. Not all digital chips do that. Sometimes the package changes where the pins are, so always be leery of that. So now let's talk about specifications. First, we're going to look at absolute maximum ratings. Now, these are not this is what you run the chip at. This is what the chip could survive. This is over the operating free air temperature range unless otherwise noted. So what they're saying is over all the temperature range that they rate the package you're using at, the chip should survive these conditions, but is not guaranteed to survive fully functional anything above this. So if we look at supply voltage, it looks like we can handle anywhere from minus 0.5 of a volt to 7 volts. Anything over 7 volts could damage this package. Continuous output current, 35 milliamps. From 0.5 volt, negative 0.5 volts to VCC, they say you can get continuous output current from an output pin for 35 milliamps. Continuous current through VCC or ground is limited to 70 milliamps. This is important to note because what they're saying is while you can pull 35 milliamps out of a pin, the max the package is allowed to pull is 70 milliamps. So you would not be able to pull 35 milliamps out of multiple pins. 2 pins would max out the chip capacity. So you're going to have to lower, if you're going to use more than 1 pin at a time, you're going to have to lower this current. Note 1 says stresses beyond those listed under absolute maximum range may cause permanent damage to the device. These are stress ratings only, and functional operation of the device at these or any other condition beyond these indicated under recommended operating condition is not implied. Exposure to absolute maximum rated conditions for extended periods may affect device reliability. So what they're telling us is, yes, the package will survive 7 volts, but we can't guarantee you will survive that continuously. So what they're really telling you is do not use 7 volts. Stay under 7 volts. Recommended operating conditions, supply voltage, minimum 2, nominal 5, maximum 6. Okay, they're saying don't run this continuously over 6 volts. Now we're going to get into high level and low level input voltages. Now this is what we were talking about in the last video when we were talking about zeros and ones. And if you remember, we were looking at this little chart I put together. And these green lines, remember me explaining that a low is not 0 and a high is not 5 volts. First of all, high could be 6 volts if you run in the package at 6 volts. But that's not what they are. They are a range. See the green bars? A low is something in this green bar here. And here's how that matches up. We're not going to talk about 2 volts at the moment. We're going to talk about higher voltage. 2 volts is an extreme case all the way at the bottom, and I'll talk about that in a minute. But here we're saying that high level input voltage, if you're operating at 4.5 on the chip, is 3.15. Now what that means is the bottom of this green right here is 3.15 if you're running the chip at 4.5 volts. So of course the top of the green is going to be the 4.5 volts, right? The VCC. So anywhere in there will reflect a high. If you go to the low 4.5, you'll see 1.35. That's the top of the green bar on the low. It means anything from 1.35 to 0 is considered a 0. So these are those values we were talking about, how these vary. Now note that the chips considered to be running on 5 volts is typical, and they don't give you that. How do you know where that would be? This is the part where they kind of expect that you probably understand this part of the deal. So, okay, let me bring this over and let's talk about it. I've got here high level, 4.5 volts operating, minimum voltage 3.15, and I calculate that to be 70%. If we look at the 6 volts at 4.2, it's also 70%. Well, that's not by chance. In reality, what they're telling you is the chip runs at 70% is the level you have to reach to hit a high. So if we reverse the calculation and we throw in knowing that it's 70% here and calculate it, we can find out that 5 volts is going to require 3.5 volts. So you can calculate out any voltage you need where the high is going to come in because you know the percentage. And it works the same on the low. If we look at the low and we come up and pull the spreadsheet up some, we can see the same thing. 4.5 takes 1.35, that's 30%. Well, 6 volts says 1.8, that's 30%. So if you take 5 and figure 30%, you come up with 1.5 volts. It's based on percentages. Now, why don't they just give you a sheet and say it's so many percentage? Well, that's where I wanted to stay away from this 2 volt. There are extremes. When you get down to the very bottom of the chip, sometimes you get variations. If you calculate up 2 volts at 1.5 volts, you're going to come up with 75% instead of 70. And so they can't just give you one, it's all 70. But in the normal operating range, the vast majority of where you'll operate will have a fixed percentage that you can calculate. So that's how that works. They just kind of expect everyone to know that. That's where we come into what's a high, what's a low. Let's talk about thermal information. They'll often give you a junction to ambient thermal resistance with these chips, and it's in units of degrees C per watt. And the packages typically will have different amounts because the area of the package is different, and so you tend to have more or less resistance to thermal energy, and more area is going to be in contact with more air, and so lower is better because we want to get less heat for the amount of power we're dissipating. So if we look at our dip package here, we can see that we're going to get 67 degrees of C above ambient for every watt we pump in. So if you're going to start pulling a lot of current from this chip and dissipating a lot of power, you have to be leery of this because 67 degrees is quite a bunch of temperature increase for a single watt. So how you'd figure this out is to know how hot the chip's going to be running. You'd say, okay, well my ambient, let's say my ambient's 30 degrees and I've calculated up I'm pulling 1 watt. Well, 67 degrees plus 30 is 97 degrees C. So you know the package is going to get quite warm with 1 watt being dissipated. This is why this information's in here and it's very important information to know. Usually you're going to get some timing parameter charts, and these are going to talk about, we discussed in the last digital program that things don't just turn on instantly and off instantly in the digital world. They slope up and down, or slew. We use the term slew a lot. Their slew rate is how fast they can go from being 0 volt to say 5 volt, from 0 to VCC. How fast can we get there? Some devices can do this very quickly. Some devices take time to turn on. You've got charts here that kind of give you an idea of what kind of timing and such, in case you're working on very critical things that have very precise timings between, maybe you have other chips that you've got to interface with and you want to know how the timing is going to fall out. Now, normally if you're not running at the extremes of their operating frequency, this doesn't fall into much of a factor for you. Okay, so then we come into the mechanical data. They start showing you the dimensions of the small outline plastic, like the SOIC and such. Here's the SOP. And then they give you board layouts. Very important when you're designing a PCB. These are surface mount. Let's get down to all these different packages and everything you want to know about them when we're working with dip. So let's get down and find our dip. Okay, here's our dip dual inline package. You get your package length, you get your width of your pins, you get the spacing. You see here it's 0.1 inch between pins, or 2.54 millimeters. The height, the profile. Notice that the legs are not straight up and down. They tend to be sprung out. That's for insertion into sockets and such. How wide they are, profile of the pin. So you get all that information in your data sheet. So these are the kind of things you need, and that's going to pretty well finish up your data sheet. I hope walking through the data sheet, showing you a few little pieces of information was useful. So let me jump over and pull a different program up, and then we'll take a look at what we're going to build for the next video. Okay, here is our little test circuit we're going to build, and let's take a look at what we've got. Down here we've got a Arduino Nano, which we're going to use to drive everything. And then we have 2 595 chips connected up in series. And you can tell that because the output part of QH comes over. Let's follow it down, and it goes into the serial of the second chip. So the data is going to come in the serial here from our Arduino, and it's going to flow through the 8 states or 8 registers of this chip and fall into the first register of this chip and start filling this chip. So we have 16 registers to work with, which will drive 16 LEDs. We've got some current limiting resistors in here to make sure that we don't try to pull more current than the chip can supply. And you see some additional LEDs up here. These are our data lines running over to run everything from the Arduino to provide the data. We've put some LEDs in there to let us see what the state of these lines are. What we're going to be able to do is we're going to be able to see what this chip is doing, and then we're going to write a little bit of code, and this code is going to operate this at a very slow speed to where you can watch the data cycling through the chip and see that everything we described works in our little circuit we designed. Now these two little things up here are U1 and U2, the 595 chips. In the schematics, often they show the power separate. These are the power for those chips. This is just the VCC and ground, the negative and positive 5 volts. The ground and the 5 volts going into these chips, it just shows it as separate for convenience, and that's what these are. And you can see all the power is connected together, and I don't show my source coming in, but of course we will power both ground and 5 volts on the breadboard. So it'll take me a little bit to hook this up and get this wired up. So I'll wire this up, get it functional. I'll write a little software, and in the next video of this series, we'll walk through the software just at a very basic level and say, this is this, and that's what it's doing, and this is doing this, and this is doing this. And then we'll go over and we'll play with our circuit and watch what we wrote operating these 595s and show how with just a few data lines, we are able to control so many LEDs. You'll be able to watch the data go through. We'll make sure that when we're done with that, you understand what you're seeing going on this board. So I really appreciate you hanging out with me in this video. I hope you're learning something from this series, and I really hope to see you in the next video.